When you install a VFD, the manual usually says to install one of these, an RFI filter choke on the motor outputs. But how do these things actually work? Stick around. Welcome back to Cloud 42. I'm James. Over the years, you've seen me install a couple of VFDs, one on my lathe and one wired up in a box for this new spindle on my mill. And you've seen me install these. These are RFI filter chokes, and this is a toroidal inductor core. And you've seen me install these on the motor outputs of the VFDs. And the ones that I used on the lathe are little ones like this. I used a whole bunch of them in both common mode and differential mode configurations. And more recently on the mill spindle one, I used a much larger choke in a plastic bracket that was designed specifically for VFD outputs, and wrapped the wires around that when I wired that up. And those are pretty expensive. The one that I used on the mill spindle was like $130, though I found them on the secondary market, maybe gray market, hard to tell, for like 30 bucks. But there are all kinds of large ferrites like this one available on eBay and available on Amazon for, $12, $13. And so I thought it would be worth taking a look at some of these, trying to figure out if these are appropriate for that application, because if so, they're really inexpensive, and everybody who can afford a VFD can pick these up really easily. And so you don't have to spend the big money on an industrial filter choke if these cheap ones that are available all over the internet are good enough for that application. So I got interested in it, spent a bunch of time researching it and looking into it, and I thought you guys might be interested in seeing it as well. So we'll take a look at some of these chokes, what we can learn about them, and then ultimately, got some test gear, we can hook them up and see how they work. So in addition to the ferrite that is already installed on the mill spindle in that box, I don't want to dig that out. I picked up a couple of other ones. This one just came from an eBay listing, and it's labeled as the material being PC40, and this is a 63 by 38 by 25 millimeter toroid. And what that means is the outside diameter is 63 millimeters, inside diameter is 38 millimeters, and the thickness or width is 25 millimeters. And that's a very common size that you find all over the place. And I picked this up because it is physically about the same size as the one that I bought that was recommended as the filter choke for the VFD that I installed. In addition to these that are all over the internet, I also picked one up from Automation Direct. And this is the same thing. It's a 38 by 63 by 25 millimeter choke. And lo and behold, it looks very, very similar. Similar size, a little bit different green color, finish is a little bit different, but are these the same thing? What can we find out? So the problem is when you buy these things, the data sheets and good data on what you're really getting are hard to come by. So there's kind of two ways that you'll find these things marketed. One way is like this one that came from Automation Direct. And I know you probably can't read this, but it says it's a Roxburgh Tor Series toroidal core. And this one is the Tor 221, and their price at Automation Direct is $13. And they recommend this for AC and DC drives, general purpose mains, filter, and pulse applications. This is kind of all they tell you. They tell you that it's a drive rated toroid for single and three-phase applications. Just here's the toroid you need if you're installing a VFD. Great, I can install it. They show you how to wire it. And aside from the physical dimensions, they really don't give you anything else. They don't tell you anything about magnetic permeability, core saturation. They don't really tell you anything. They don't even tell you what the material is that the core is made of. There are dozens of core materials designed for different applications. So this is one way you find them, saying, buy this, this is for a drive. And again, these can be industrial application, from industrial suppliers for a ton of money, or discount ones for, $12, $13. The other way these come, when you typically find them on eBay or on Amazon, is they'll tell you what it is. Like in this case, it says the material is PC40, and you can get data sheets for that. And these are data sheets that have magnetic permeability curves and magnetic flux density saturation numbers and all kinds of information about temperature derating, but nothing about applications. So is this appropriate for an EMI filter on a VFD? Well, if you've got a degree in electrical engineering and you understand all of this stuff, you can probably figure that out. But for the layperson just buying something, even if you've got hold of this data sheet, you don't know, is this what I need for a drive? Well, I could try to compare it to this one that's spec'd for a drive, but I don't have any data on this, so I don't really have any way of comparing them. So I wanted to know, are these things the same thing? Can you just buy these cheap ones off of eBay and expect them to work like the ones that are spec'd for the application, or like the ones that are actually supplied from industrial suppliers for this application? And I decided to do some fiddling with them and see if I could find out. Now, the normal way that you would characterize an inductor is with a tool called a vector network analyzer. And they can be real expensive. You can get some cheap ones that are specific for RF applications, but for the low frequencies that we're particularly concerned about for these, they're not particularly suitable. So I actually took these cores in. One of my coworkers has a Bode 100 vector network analyzer, which is like a $5,000 piece of gear that I don't own. We put 4 turns of wire around each of these to actually make an inductor, and then put them on the network analyzer and swept frequencies from 100 hertz, which is kind of down in the power range, up through 25 megahertz, which is well up into the RF noise range, just to see how these things behaved. Now, I can take measurements with an LCR meter and measure the inductance at a few frequencies, but a vector network analyzer like this can give a lot more data. And this is basically what we found. The green and the orange lines are the plots for these 2 different toroids. And as you can see, they behave almost exactly the same. What you're looking at here is a plot first. This first line that comes over and then drops to about 0 is the inductance. So if we start at 100 hertz, the inductance is right up here around 200 microhenries. That's with 4 turns of wire around it, which is how it's recommended to be used in the VFD manual. And that continues up through 1 kilohertz, 10 kilohertz, 100 kilohertz, and then right around 200 kilohertz, the inductance suddenly falls off and goes to almost nothing. Now, this is normal because in an inductor, it's very common once you get above a certain frequency that the capacitance between the adjacent wires in the coil starts to become dominant, and where it was an inductor that was blocking these frequencies, as you get to a high enough frequency, it becomes a capacitor essentially and starts passing them again. The other plot that's on here is the impedance. So you can think of this like resistance, and it's denominated in ohms, and you can think about this as the resistance to current flowing through it. It acts like a resistor in a circuit. It's not exactly resistance because the current and the voltage are out of phase with one another by about 90 degrees. So what happens is at very low frequency, there is very little impedance. So this looks like a dead short. So low frequency signals like the 400 hertz power signal that's going to the motor, any of those kind of low frequencies don't see very much impedance at all. They flow right through the toroid, right through the coil. And then as the frequency increases, this is logarithmic, up to 1 kilohertz, 10 kilohertz, 100 kilohertz, this starts looking like a big resistor. Of course, out of phase, it's an inductor, and it's looking like a large impedance that actually resists the flow of that high frequency energy. So it blocks, in essence, the noise currents that we're trying to block. And so that's exactly what we would expect. As frequency goes up at this constant inductance, the impedance goes up, and so as the frequency goes higher, it blocks more and more and more of those higher frequencies. And we'll hook that up here in a little bit and demonstrate that. But then an interesting thing happens. Above 200 kilohertz, the inductance falls off dramatically. So you would expect that the impedance would also fall off, but it doesn't. It levels out up here around, let's see, where are we? We're up around 200, 300, between 300 and 400 ohms. and the absolute value of the impedance just sort of levels out and goes straight. So there's something else going on here that is making this continue to block these higher frequencies even after the impedance falls. Now this is ideal, this is exactly what we want, but it's a little odd. What's going on here? Well, because I have a vector network analyzer at my disposal, I could create some more plots. So this is the same impedance, it goes up and then mysteriously continues even after the inductance falls off. But what we're looking at here is this second set of curves is the phase angle. So like I said, the current and the voltage are out of phase in an inductor. In fact, this up here, the scale's on the right-hand side, this is a plus 90 degrees, so it's 90 degrees out of phase. And at this point where the inductance falls off, you can see that the phase angle comes back down to around 0. Well, a 0 phase angle is characteristic of a resistor. So what's happening is it's an inductor and it's blocking these frequencies increasingly with higher frequencies, so it's blocking the noise. But then at the point where a normal inductor would become less efficient at that, it actually turns into a resistor. And what's happening here is that the particular material that they chose for this core, carefully chosen for this application, becomes highly inefficient at those frequencies. And instead of returning the energy from the magnetic field as it's oscillating, that energy in the magnetic field that builds up in the material is actually then converted to heat. So it becomes less efficient and dissipates that energy. Hence, it continues to have high impedance and continues to act like a resistor that then blocks those higher frequencies. So I just find this kind of stuff fascinating. I'm not an electrical engineer by training. Everything I know about this stuff I've taught myself, or I've picked up from online sources, or I have friends and coworkers who have taken time to explain things to me, and I find all this stuff fascinating. So when I see something like this and the instructions say, take this round thing, poke some wires through it, and it'll make the noise go away, my brain can't leave it at that. I want to know why it makes the noise go away, and I want to understand it. And so I just find this kind of stuff fascinating, and since I was diving into this anyway, I figured I might as well throw together a video and share that experience with all of you. So I have some test gear here. Let's wire one of these up, send some signals through it, and see it actually do what these plots say it will do. What I have here is an old HP 3325A synthesizer function generator. This is an instrument that can generate a bunch of signals, but for our purposes here, it can generate sine waves from about DC up through 20 megahertz. And we're going to use this to generate signals to send through one of these coils, and we'll measure the results on my trusty Rigel DS1054Z oscilloscope. I apologize for the noise that this makes. It's old gear and the fan is not quiet. Now, sadly, when I pulled this instrument out a couple of weeks ago, when I first attempted to film this video, it did not work. It did not power up anymore. All it did was blow fuses because it's old and some components in the power supply had expired. But happily, I was able to fix it because smart. So now we've got a functioning instrument. We'll start out generating, let's just start with a 60 hertz sine wave at 1 volt RMS. And we can see that up here on the oscilloscope. I just have it piped out of the output of the signal generator through this cable to the oscilloscope. One thing that's important to note is this instrument has a 50 ohm impedance output, and it expects to go into a cable with a 50 ohm terminator. So I have a 50 ohm terminator on the T so that the amplitudes generated by this will read correctly on the scope. And you can see here we have a nice sine wave. Frequency is right about 60 hertz. I'm not sure how much I trust this. It's close enough for these purposes. And the RMS voltage we see here is 986, 87 millivolts, so about a volt. That's what I had programmed in here. So that's 60 hertz. We can bump this up to 1 kilohertz. And I just reset the voltage. Let's try that again. 1 kilohertz. And now we have a 1 kilohertz sine wave, still at about a volt. We could go up to 1 megahertz. And now we have a 1 megahertz sine wave, still at about a volt, and we can take this all the way up to, let's just go to 10 megahertz today. And so here's our same 10 megahertz at about a volt. So running it straight through the cable, we're seeing this instrument producing exactly what we wanted, all of these different frequencies right at 1 volt RMS. So we'll go back down to 100 hertz. And start here. Now, let's put the inductor in series. And let me draw a picture of what's going on here so you can understand what's actually happening. So we've got an AC signal source that has that's outputting an AC signal. Because this is a 50 ohm impedance, we can think of this as having a 50 ohm resistor inside, and that comes out to the connector. And now we've run that cable all the way through to another resistor also 50 ohms. So we've just connected this straight across. I'll leave that open right now, but we've just connected this circuit. So we've got our generator going through a 50 ohm resistor that's inside the generator. It's a 50 ohm impedance source going across a 50 ohm resistor, which is the terminator, and then we are measuring with the oscilloscope at these points right here. And so we see that voltage. And what we're going to do is we're going to put our coil in series right here. So if this is essentially a closed circuit, we should see exactly the same voltage. But as we increase the frequency and the impedance of this coil goes up, it's like inserting a resistance, a 90-degree out of phase resistance into this circuit. So the current flowing through here will be reduced, just like we expect it to reduce the noise current in the motor wires and in the motor bearings. And the voltage we see across this resistor should go down. So let's hook it up and try that. So I've got 4 turns of wire wrapped around this, and I've got open ends, and I'll just break into this cable. And I've just got BNC connector to just clip leads, and so I'll put one of those on each side here. I'll clip the grounds together, so the ground connection goes straight through, and I'll clip the red leads onto the inductor. Okay, and our signal's back, and you can see we're at 100 hertz, and we're right up here around 958 millivolts, so we're still at right about a volt. There's a little bit of loss even if you just connect these together. You can see we're at that same 958. I don't even have the inductor in the circuit. And that's because there is some inductance and capacitance just from coming out of the coax cable into these separate leads. But for all intents and purposes, we're still at about 1 volt. So looking at this curve, if we go up to 1 kilohertz, we should see the impedance starting to go up. So let's do that. 1 kilohertz. And again, we're not seeing very much impedance. We're at about 965 millivolts, so there's not much change yet. Let's go up to 10 kilohertz. Up at 10 kilohertz, we're still not seeing very much. Again, this is log scale, and it's log scale on the impedance as well. So even at 100 kilohertz, at 10 kilohertz, we're still only talking about like 10 ohms. But we're getting a little bit more impedance. We're down to 953 millivolts. Let's go to 100 kilohertz. And now we're starting to see this fall off. You can see at 100 kilohertz, we're down to only 540 millivolts, because what's happening is this impedance has gone up, and we've got 100, 150 ohms of absolute impedance in the middle of this circuit. So it's working as a voltage divider with this load resistor, and so the actual current that's flowing through here that we're measuring as voltage is going down. And if we continue up, we can go to 1 megahertz, and you can see this has dropped even further. Now we're down to 233 millivolts, so less than 25%. That's at 1 megahertz. We go up to 10 megahertz, and we see about the same, 270 millivolts. And that's because we got up here to 1 megahertz, and this impedance is now leveled off. So we went from 1 megahertz to 10 megahertz, and we didn't see much change. So we're seeing exactly what we would expect here. So what's happened is we took our 1 volt signal, and think of that as 1 volt of common mode noise, and the voltage doesn't matter. But of that, we've taken out 3/4 of it just by putting this toroid in series with it. But down at the frequencies that we care about, like 400 hertz, which is the maximum frequency of the motor, we haven't affected the signal at all. Here we are at 999 millivolts. So we still have, this is doing exactly what we want, which is passing the energy that we need for the motor, or the low frequencies that aren't an issue for noise are passing right through it, but the high frequencies that generate interference or generate capacitive coupling and flow through the motor bearings are being blocked. Now, that's if you use just an inductor. Now, if you really want to talk about filtering, you wouldn't do this on your VFD, but if you really want to talk about filtering, if you look at the little circuit diagram on an actual noise filter, they don't use just an inductor. They also add a capacitor. And so you'd have a capacitor installed here. And this small capacitor then, just like an inductor, increases in impedance as the frequency goes up, so this begins to block more of that high frequency signal. A capacitor decreases in impedance as the frequency goes up, so it will tend to conduct at higher frequencies. So if you set up a filter like this so that you have the inductor in series and you have the capacitor in parallel with the source, high frequencies will see this as a higher impedance, a resistance to flow out to the load, and they will see a low impedance path back to the source or to ground through the capacitor. And so you can get a much more effective filtering if you have a capacitor in here. Now, I think most VFDs are going to have this capacitor inherent in the design, but I thought it'd be interesting to go ahead and hook one of these up and just look at the effect that it has. So I have a little capacitor here. This is actually an X2 series safety capacitor. This is not what you would install. You would want a Y series capacitor to go between a signal and a ground, a safety ground. But I have this handy, and so we will try it out. Let's just measure, see what we've got. This is 190 nanofarad capacitor. Can you read that? I can read that. 189.97. And let's go ahead and put that in the circuit here. And we'll just connect it between the ground and the upstream side of the coil. See if I can do this. The answer is no, I cannot. There. Okay, so all I've done is I've just attached this capacitor across here to shunt the higher frequencies around this circuit rather than through that resistor where we're measuring the voltage. And let's see what happens. So down here at 400 hertz, we are still at our 1 volt, which is exactly what we would expect. We expect this to not have any effect at low frequency. And now let's step the frequency up and see what happens. That's 400 hertz, bump up to 1 kilohertz, and we're still at 990 millivolts, 10 kilohertz. And again, still not much. This is the frequency of the carrier wave that I'm using with the VFD in my spindle. 100 kilohertz, and now we start to see the filtering kick in. In fact, at 100 kilohertz, we've dropped all the way to 120 millivolts. So this is dramatically different. Without the capacitor, that's 556. With the capacitor in circuit, 120. Let's keep going, 1 megahertz. And now we're down to the point where we can't really even measure this. Let me kick the scale up. So you can see this is really fuzzy because I've amplified it significantly. We're talking about 5 millivolts, so we're down to less than 5%. And if we go up to 10 megahertz, then we just we just have noise. I can't even, the oscilloscope's not even able to sync on it or measure the voltage because this is just all over the place. Drop this back to 100 kilohertz where we have a little bit cleaner signal. So that's how a filter works. You would never actually hook this capacitor up, but I just thought this was interesting, again, because if you look at the EMI filters that I installed on the inputs to the VFDs, they have a circuit very similar to this. Most of them have two phases where they've got the common mode choke across the two lines of the incoming power, and then have capacitors across the input and the output and between and to ground in several places. But this is the effect. What they're doing is they're taking that noise, giving it a low impedance path back to the source so it doesn't go out to the load, and then adding an inductor to add impedance at high frequency to prevent the signal. And the signal is going to take the path of least resistance. It's going to flow, most of the current of this noise is going to flow through the short circuit back to the source and not actually go out to the load. So this is how an EMI filter circuit actually works. Pretty cool. Well, I was just doing the research on this because I know that toroid core that I showed in the video wiring up the spindle VFD is an expensive part at $120. I figured there had to be some cheaper options. These things are all over eBay, and I wanted to figure out if I could come up with some better options for all of you out there if you want to do this project. And I found a couple here that are going to be good. I will put links down in the video description. The Amazon link or eBay links will be monetized. I'll make a few pennies if you actually use one of those links and buy something. The Automation Direct link is, I don't have any affiliation with them. I don't make anything from that, but they are a good option, especially if you're ordering other stuff. You do have to pay shipping on these in addition, so the price is a little higher, but if you were already ordering stuff from them, these would also be a good option. So I hope that's useful. If you enjoyed this video, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.